Hello everyone, welcome to Statistical Foundation for Big Data Analysis. We begin module 5 today. In this module also we continue our discussion on statistical learning theory. So in first lecture of this module we will discuss bias variance trade-off. So recall that in what we discussed in our first module on statistical learning theory, that is module 4, this whole process of drawing knowledge, drawing inference about a population based on a data using a particular algorithm. So you will have a data set x1, y1, x2, y2, xn, yn. This will be a sample drawn from some probability distribution of x and y, joint distribution of x and y. For the sake of discussion, we assumed y is just single variable, random variable, that is y takes real values, and x is a vector valued random variable, random vector, that is x has multiple features. We want to find a rule for y based on x, that is y equal to hsx, which will model y in terms of x based on this sample S, drawn sample S. Now, the point of statistical learning theory is to study the algorithms. After all, when you want to find a model for y in terms of x based on a particular drawn sample, you observe the sample, go through some steps, finite number of steps, and come up with a formula, or let's say even steps of formulas. It can be piecewise kind of thing, like if y takes x takes this, these x, the values of x belongs to this group, y will be expressible by this formula. If values of x belongs to that group, the y will be expressible using the some other formula. This kind of thing is also allowed, but nevertheless it's a process through which this hs is decided. This is a rule. I mean, instead of saying formula, it will be better to say we find a rule that gives you y in terms of x. But the game is that the only way you can come up with hs, the only way the algorithm can decide on hs is based on the sample. There is no other information the algorithm has at its disposal. So this is the process. So obviously the rule that will come up will depend heavily on the sample. Now we discuss various aspects of this process in our module 1. We discussed the two sources of potential difference, potential error or potential difference between the actual value of y and the predicted value of y. The difference between predicted value and actual value potentially comes from, we discussed that like it potentially can come up from two different sources of let me say idiosyncrasies in our algorithm. One, the algorithm inherently is focusing on certain features which does not match fully with the actual feature of the population. So, for example, if the population is quadratic and the algorithm only focuses on linear, then the data you have collected, even if the algorithm explains that particular data well, it may not be able to predict some other future data. If you draw some other future data from the same population, it may not be able to predict that future data well. And as a matter of fact, it may, so if you are inherently assuming for an inherently quadratic population, you are fitting a linear model, there will be a certain deficiency in your modeling process which will show difference between average predicted value and the average actual value. So this inherent assumptions that algorithm makes, inherent theoretical assumptions algorithm make, which differs from the actual behavior of the population, that gives rise to something called bias. And secondly, another thing that creates problem for us is so called variance, where the algorithm itself becomes heavily dependent on the particular data set you collect. The peculiarity of the algorithm is such that it is too much focuses on the data set, the peculiarity of the particular data set, then again there will be a problem. For example, if your data set is of size 5 and let us say if you are trying to fit a degree 7 polynomial on that data set, you will get a perfect fit. But guess what? For any data set you draw, there will be a perfect fit. So, when you start with a particular data set and you fit a polynomial which passes through all the data points, you draw a future data set, it will definitely not explain that well. So, just to give you a picture of this process. So, suppose this is your population and let us say you collect these 4 data points, it is here. Now, suppose you fit this using this curve. Now, obviously, if you pick up points here, here, it will clearly not pass through that. There will be, in fact, for these kind of points, the difference between predicted and actual will be pretty high, and then the moment you go this side, this will be really high. So, this will really not be, so these are very big errors that you will get. So, obviously, if your data point is, your algorithm is focusing obsessively on the given data point, and it may not be doing knowingly, but let us say just to be hyper cautious, you have taken a very large degree polynomial, degree larger than your available data, size of the available data, then already it will give you an overfit in the data. So, if the algorithm becomes obsessively sensitive to the data, then the rule that will be produced by that algorithm based on different data set will be very different from each other. And this difference, the average predicted rule, the difference, the squared difference between a rule predicted by the algorithm based on a particular sample and the average predicted rule, where average is taken over all possible sample, this average squared distance between these two, average taken over all sample again, is called a variance. So, we discussed all these things and in last module, and we saw actually in the last class we saw some examples of low bias, low variance model, which was a fantastically good model, but that was, well, that was a very specialized scenario where underlying population was such that x y indeed had a linear relation. The relation between x y could have been explained modulo some intrinsic error terms which was centered around 0 and constant variance. The relation between x y modulo that sort of error term could have been explained by a linear relation. X y had more or less linear relation between them, and you were trying to model it by a linear model. So, the model was actually guessing the behavior of the population correctly, and the model itself was linear. The population was linear, the model was linear. So, that kind of low bias, low variance model happened under the situation where the algorithm was actually predicting the nature of the population correctly, and that nature, that common nature of the algorithm and the population was linear. Linearity was extremely important, and this we will learn in more details in the next module, on module 6, when we actually discuss the linear model scenario in full details, where we will actually derive this thing called Gauss-Markov theorem, where it will be shown that actually the by least square fit, which we also saw a little bit in some earlier module when we were discussing basics of statistics. I mean, we discussed a simple least square fit where there were only one x and one y, and you were trying to fit y in terms of x. So, the coefficients you get are actually unbiased estimator of the underlying population coefficient. So, if the population is linear and you are trying to fit a linear model, then what you get is an unbiased estimator of the population coefficients in terms of this least square coefficients. So, this is Gauss-Markov's theorem, and well, it says something even more, and we will get there, in next module. But under that situation, we got a model where low bias, low variance. Then we saw a case where you have low variance yet high bias, and that model was exactly same thing, linear, linear relation between the underlying population, and you were also fitting a linear curve. Your also model was also giving a linear fit there, but except doing the least square fit, that is taking the curve which taking the line which describes the collected data best, you are intentionally, artificially, you are adding 100 or some jump, like you take that line, shift it by certain things. Now, basically, I mean, this was obviously a rigged example, because you knew the line explains the data perfectly, you are just intentionally shifting to make sure that it does not explain the data. But I did that just to explain what really algorithmic bias is. Here there was the algorithm was putting certain things, algorithm was searching things which was 100 shifted from the actual center of the population. So, it was looking away from where it was. So, this is essentially algorithmic bias. Of course, just shift does not change variance. So, the variance of when you take various samples, you are essentially the variation will come from this 100 shift will not affect the variation, because the variation ultimately comes from everything, not just from the shift, but everything other than that, not from the shift, but everything else, and everything else there was actually the fitting the least square curve. So, variance was same as the least square variance, which was very low. So, that was giving you a low variance high bias model. An example of a low bias high variance model. Now, that was something we discussed using that splitting the sample into two parts. Suppose you are fitting a least square curve using one part of the sample, let us say you took a sample of size 3 or more, you fit a least square curve from data point 2 to n. Leave aside the first data point, that is still a least square curve. So, if that was your sample only, that will give you a low bias low variance model. If that was your you take the 2th sample point to nth sample point, we discussed all these things in last class, but just to recall, if you take the 2th sample point to nth sample point and fit the least square curve, it is still a least square curve. You are assumption on the population was the same, it was still a linear relation population. So, least square curve will fit as in the case of first example of low bias low variance, and it will be low bias low variance again. But what you are doing, you are adding an extra variance, where using the first data point to add an independent component. Independent will basically make sure the variances just add up, and that component had 0 bias. So, you chose that component to have 0 expected value. So, the bias being this expected value, this will not add up to that, but it had some independent variance, and it was being the first data point I was choosing, because I instead of choosing it let us say for half the data points and so on, because if you are choosing involving the sample size there was a chance that the variance will get divided by n, and as you take large sample that may get smaller, but we did not do that, we just took one data point to create that component. So, that constant variance will remain, and if your x has higher variance, which in that case it was, because x was basically uniform 0 40. So, which was a kind of a big interval. So, it was giving you high variance. So, that amount of variance will lurk there. So, that was the example of high variance low bias model, and high variance high bias model will be just take this high variance low bias model and add an 100 to that. So, that will just shift it, and already has high variance will add lots of bias also. We discussed all these things in last class. I was just quickly reviewing what we discussed already. So, these are the definitions, we kind of discussed it to death. So, today's main agenda today is to express this term, the total test error, in terms of bias and variance. Okay. So, let us move on. So, today's agenda, so these are the formulas. Today's agenda is to express this total error, the total taken average taken over all possible sample, all possible x's and y's, and then you kind of average the squared difference between the predicted and actual. So, if you want to study this expected test error, this is the sort of the grand error, grand average error. We will see how this error actually consists of bias and variance only. Well, sort of, we will see today. Basically, this decomposition theorem of this test error. So, this will be potentially, I am just going ahead of the class. So, we will be able to show that this grand test error is actually expressible in terms of sum of three components. Your variance we discussed, your bias, and something that is unrelated to the algorithm. We call it noise. So, this is why this is unrelated to the algorithm. So, here Gx we used an introduction for the we use a new notation for y bar x as Gx, where y bar is our y bar that we are using in last class, the conditional expectation of y given x. Note that you are taking the expected value with respect to x and y of Gx and Gx minus y. So, Gx is a function of x only. So, for all I, for all y, if you take the difference between Gx and y, that is the you take the difference between actual value of y, the square difference between value of y from its conditional expected value with respect to x, and then take the square of that and take the expected value with respect to the whole population, the joint distribution of x and y. This is called the noise. This has nothing to do with algorithm. This is completely dependent on your population. This is coming from population. Your algorithm cannot do anything about it. So, this is why this is called noise, that is no algorithm can potentially touch it. For any algorithm, there are several layers of this theorem. We will discuss the proof of it, but if you closely for now look at the result, any algorithm, this is a reasonable measure of performance of this algorithm, of any algorithm. This is low, this total error, grand error low will mean that the algorithm reasonably performs well for an average sample for most xy. So, for a randomly chosen sample, as long as there is the sample is a representative sample, an average sample, because remember we are kind of taking the average over all possible samples also. So, for an average sample, so this value is less means what? Average of some certain thing is less means what? Average of certain thing is less means what? There may be a few random outlier big points, but on an average most of the things are less. So, this is less means for most samples and most population points x and y, the predicted value in terms of this algorithmic rule HS. So, for most sample, the rule it produces gives you good estimate for most y's, for most xy. So, let me rephrase it. So, this error is less means what? What does it mean to say average of certain thing is less? Average of certain thing is less means there may be a few big outliers, but most of the points have less value, average less, that leads to average being less. This is less means for most samples, the rule produced by the algorithm HS, most samples S, the rule produced by the algorithm HS predicts y accurately for most points xy. So, that is, for most samples S and most points xy, the predicted value HSX is very close to actual value of y. So, this less means that. Now, this for any algorithm will be sum of the variance that we defined earlier, that is the average squared distance between predicted value and the average predicted value, bias, squared difference between average predicted value and average actual value, that is the h bar x and the expected value of y given x, plus something that is coming from the population. This is coming from population. So, let me just, this is coming from population. Now, no algorithm can beat this one. The error, so call this noise N, error greater than equal to N always. On an average, you potentially cannot be better than this one. That's the key takeaway from this observation, that if you somehow by magic knew that what this is, that will be your potentially best prediction. So, in general, for any population, any prediction, even if you make bias and variance 0 miraculously, this will be lurking. So, you cannot do better than inherent variability within the population. So, all predictions, for all algorithms, the average prediction error taken over whole population as well as all possible sample will always be greater than equal to noise. But other than the noise, there are only these two things. So, in last week you might got really bored with the repeated discussion on what is bias and what is variance and what are those, why conditional probability was being so much emphasized, why rule of iterated expected value was being emphasized so much. Here is the reason. The actual what the algorithm can do at best is to keep these things on check. If the algorithm potentially keeps these two on check, that's the best any algorithm can do. The other thing that is involved is actually this indecomposable, untouchable error component that comes from the population, that's involved in prediction game itself. So, this error will never go away. Whatever you do in the algorithm, you cannot beat this one. So, this is the sobering lesson from this theorem. And actually what happens in real life, I mean, it probably was clear from some of the examples we were showing last class. I mean, potentially you cannot really contain these two either. I mean, to keep both of them under check, what you really needed was actually a very idealistic situation where you really needed to predict something, a pattern in the population exactly. So, you knew the population followed linear rule and you were actually doing a linear prediction. So, that was the only case you got low bias, low variance example. So, in real life what happened is that, like, potentially you can control at most one of them. To keep bias under control, you end up increasing variance. To keep variance under control, you end up increasing bias. That is what happens in most cases in real life. But even if you somehow magically control these two, you cannot control the noise. So, let us just recall this linear case, since we were emphasizing a lot on that. So, in the linear regression case, the model was basically your data points yi's were a plus bxi's, and these were variance were for each of epsilon. So, the model was basically y equal to ax plus b, where ax plus b plus epsilon y was ax plus b plus epsilon, where epsilon followed some distribution. So, epsilon need not be normal. So, what you knew that expected value of epsilon was 0, variance of epsilon was sigma square, and you got the data x1, y1, xn, yn. That was your data. That was the linear model, and you were doing this with least square. Here, this one will be for every point, this one will be your mean square error. That will be your average error. So, you will basically take expected value for a particular point x naught, you will take the expected value of predicted y, expected value of actual y for x naught, and this predicted value in terms of x naught. So, that will be your mean squared error. So, that was for linear regression model that we discussed so much in while giving the last examples of last class. This error we will see will be broken into bias and variance. So, this will be basically variance of this model and the bias of this model. In this least square case, what was happening, that this bias was 0. So, for this model, the bias is 0, and the mean square error is just the variance of this, and one can actually calculate the variance of linear model coefficients. One can calculate variance of these things. So, basically the error in the least square modeling only came from this variance and this irreducible error, not error sigma square, and in this case sigma square is actually the error of epsilon. This is the pure sigma square. So, this is how the bias variance decomposition, or the decomposition of error into bias, variance and noise happens in case of the linear model. Now, let us see why this is also true in general, the theorem we discussed, the bias variance decomposition theorem. Let us actually do a careful proof of this. It is not super difficult actually, just to again carefully analyzing the conditional expected values. So, this is your grand error. You are taking average with respect to the whole population of x y as well as all possible samples of the predicted square difference between predicted value and actual value, predicted value for y HSX and actual value for y, which is y, the square difference between. Now, of course, you can subtract and add age old tactics. So, you subtract h bar x, that is the average predicted value, and if you subtract that, you have to add, and then you separate these things in a square formula, a plus b whole square formula. So, you write this expression as this minus this within bracket plus this minus this within bracket, this sum of these two things whole square. Now, if you split it, you will get the sum of square of, oops, just one second, you will get the square of the first term here, square of the second term here, and the cross product term. The cross product term, it turns out it is 0. Let us see why the cross product term is 0, the middle term. So, to do average over whole x y s, what you can do, you can keep x y fixed and first take the average with respect to s. So, now when you are taking average with respect to s, note that this term is s free, this is s free. Why? H bar, in H bar already S factor has been averaged out. The X factor in H bar has been averaged out. What is H bar? H bar x was expected value with respect to f of hsx. So, it only depends on s, it only depends on x. You have taken the s values, hs values for x for all s and taken average. So, it only depends on x, it does no longer depends on s. So, s factor has been averaged out. Please remove my face, so in h bar no s is involved, and y is of course y, it just comes from population. So, this is why this term comes out of the bracket. This term comes out of the bracket. Now that this term has come out of the bracket, what you are doing is looking at this. But what is the expected value of? So, this is again expected value of hsx minus h bar x. Now, when you are doing this, this is expected value of hsx minus expected value of h bar x, but h bar is free of s. So, this is just h bar x, but if you take expected value of hsx with respect to x, you get h bar x. So, h bar x minus h bar x, this gives you 0. This is 0 inside. So, whatever happens here does not matter, because everything times 0 is 0. So, the middle term vanishes. Now, you just got these two terms left. This term is your variance term. Already one term in the sum, it was sum of three things: variance, bias, noise. Variance has already appeared. Let us deal with this term. Again, you subtract gx and add gx. Remember, gx was, I introduced a new term gx for expected value of y given x, which we were using as y bar x. I intentionally for this talk I am introducing this notation gx, because just to emphasize that this is just a function of x, y has been averaged out. Just like h bar x is just a function of x, s has been averaged out. Now, again break into three terms: square of the first term, square of the second term, plus the third term. Already note that this is your bias, this is bias, this is expected value of average squared difference between predicted value of y and average value of y. This is this term, this is bias, this is noise, this is the population coming from the population. All we have to show that this is 0. Why? Let us discuss that. So, once we have established that this term is 0, we get the breakup in the theorem. Now, in this middle term, you have expected value with respect to xy of h bar x minus gx times gx minus y. So, this is where we ended in last page. So, you are taking expected value with respect to xy. See, this is, first of all, this term is s free. There is no point in talking about expected value with respect to s part is gone. So, now you have to just calculate what happens to this term. So, this term you first take expected value with respect to y, the average the y part out, then take the expected value with respect to x. So, when you are averaging with respect to y, keep the x fixed, that is you are doing it with respect to the conditional distribution of y given x. So, I am just writing, just to avoid cumbersome writing notation, I avoided writing it. It is just basically expected value of y fixing x equal to x. So, x is fixed when you are doing that. So, now because you are doing it with respect to y, this term which is just a function of x goes out and bingo. All you have to observe expected value of y of expected value of with respect to x of y given expected value of y of expected value of y given x minus y, where you are taking expected value with respect to the conditional distribution. When you are doing this, it is an expected value, so it splits into the sum, expectation commutes with sum minus expected value of y. But what is this? Law of iterated expectation says expected value of with respect to z1 of expected value of for all random variable z1 z2, for all z1 z2, expected value with respect to z1 of expected value of z2 taken conditional with respect to z1, expected value of z1 given z2 is expected value of z1. This is a random variable that depends only with respect to z2. So, when you are taking expected value of this random variable, when we are taking conditional expectation of z1 given z2, you are doing it with respect to the distribution of z1 given z2 equal to z2. So, this is a function of z2. Now, you are taking this with respect to the distribution of z2. So, when you do this expected value of conditional expected value, you just get the unconditional expected value back. Here exactly that is what you are doing. You are taking expected value of conditional expected value of y given x. So, you get expected value of y, and you already have expected value of y, you get 0. This is precisely what is happening here. So, this gives you this decomposition of our grand error in terms of bias, variance and indecomposable error component in the population. So, with this observation that we have derived this for every algorithm, I stop. Thank you.